All right, so today we took what we learned about Newton's second law over with our experiments, and we applied it to a tool that we call free body diagrams that allow us to analyze situations and then make useful calculations. So let's start off with a reminder of Newton's second law, the relationship between acceleration and the net force, or the sum of all forces acting on an object, and the mass of the object, as seen in these two forms of the same equation. And then let me give you a definition for free body diagrams. I define free body diagrams as visual representations of all the real forces acting on an object. And so we took several scenarios, situations, and looked at the situation and drew a free body diagram and then used that to analyze what was going on with the forces and the resulting acceleration. So, for example, at first we set a baseball at rest on the table, and we started analyzing, okay, well, what forces are acting on that baseball? So we start off by drawing just a representation of the baseball. I'm definitely not an artist, and so just any circle will do. And then what real forces are acting on the baseball? Well, so long as you're near the planet Earth, you're going to have the gravitational force of the Earth directed towards the center of the Earth, which normal people call down. And so I've drawn an arrow originating at the center of mass of the ball and pointing down. And then there's several labels that we could use to identify what that force is. You'll see variations of F sub g or F sub gravity. And then if you ask the common person how they would describe what the gravitational force on an object was, they would call it weight. So sometimes you'll see capital W. I prefer the one that comes straight from Newton's second law, since forces are the product of masses and accelerations. If the only force acting is the gravitational force, then it's going to have the quantity of the mass times what the acceleration in the gravitational field of the Earth is, which is g. And so I always use the label mg. And that's helpful when we set up statements later and do calculations. But you can see any of those labels for the downward gravitational force. And then, of course, if it's at rest on the table, there's another force that's acting in the upward direction. And we have several labels for it as well. We could call that the force of the table. We could call it F sub capital N. And I'll tell you what that is, because I use that capital N by itself as my label. And that N stands for the word normal. And normal has a very specific definition in physics. It's not like its normal use in English. Normal in physics always means perpendicular to. And so the table is pushing up on the baseball, perpendicular to its surface. And so it's exerting what we would call a normal force. And a normal force is simply that. It's a pushing force where the push is acting perpendicular to the surface that's doing the pushing. And so, again, you could call it force of table. You could call it in any number of labels that are appropriate. But I prefer the normal force because it specifies that this force is perpendicular to the surface of the table. All right, so then what do we do with this? Well, the next thing I want to do is I want to identify a positive direction. And as you know, I've always stated that Rule 1 says that we should make the acceleration along an axis and positive if possible. Of course, you can anticipate if the ball's at rest, there's not going to be an acceleration, and so it doesn't matter whether we pick or up or down as positive. And so we just chose to pick down as positive, I guess because we were in the habit of doing so for projectiles. But again, it doesn't matter. Up or down as positive will work. But then once I choose that positive direction, I'm going to be consistent. And I'm going to write what I call an F net statement. In other words, I'm going to write that the sum of all forces acting, in this case, in the vertical direction. And then I'm going to list them. I'm going to name all the positive forces and then all the negative forces. In this case, down forces, which are positive, are mg. Up forces, which are negative, is the normal force. And so my F net statement, or the sum of all forces acting on the object, in this case is mg minus n. Now I should note that if I had chosen up as positive, my F net statement would simply be normal minus mg, because I just reversed the directions of the positives. And as you'll see in a second, again, it makes no difference whatsoever. So then that's the second major step. After drawing the free body diagram, I'm going to write an FNet statement, and notice it's based on that free body diagram. I can't stress the importance of this enough. Always start off by drawing a good free body diagram with forces pointing in the right directions, and then after determining a positive direction, write a clear FNet statement of all the forces acting on that object, being careful to make positive and negative notations based on those directions. And then the third step, again, equally critical, is after I've written that FNet statement, I go back to Newton's second law, which says that the sum of all the forces always equals ma. And so on the left side of this equation, I'm going to substitute ma for the net force. So ma in the vertical direction then equals what's on the right, mg minus normal. Well, then what's true about the ball? It's at rest, and therefore the acceleration in this scenario is 0. And if the acceleration is 0, then the sum of all forces equals 0. The left side becomes 0, and I can prove then that the normal force, in this case, is equal to the gravitational force. Now, that doesn't have to be. It's not always the case. But for this situation with the ball at rest, I've demonstrated that those two forces are equal, and we already knew that they were opposite, and so of course if two vectors are equal in magnitude and opposite in direction, they're going to balance each other out or cancel each other and result in a net force of 0, and that results in the ball staying at rest. Now again, that just proves that the acceleration is 0, and since it was at rest to begin with, then its motion's not changing, and so with an acceleration of 0, it remains at rest. All right, so, and then we said, well, what would the magnitude of that force be? How much would it be? In this case, we identified that the mass of the baseball was 140 grams. If I convert that to kilograms, I get 0.14 kilograms, and then I can plug that into mg and find the weight of the baseball, which 0.14 times 10, and once again, even though when we're doing experiments we want to use 9.81 as the gravitational acceleration or the gravitational field strength, I'm perfectly fine with using rounded to 10 to make our calculations easier on all hypothetical problems. And so in this case, the weight becomes 1.4 kilogram meters per second squared, but that's a mouthful, and so we said, well, let's honor Newton by naming the unit for force after him. And so 1 kilogram meter per second squared is also known as a Newton, and so the force of gravity on the ball is 1.4 newtons, and since our statement proved that the two forces are equal, I know that the table's pushing up with a force of 1.4 newtons at the same time, and that's resulting in the baseball remaining at rest. So then we did a different scenario. I took the baseball and I started lifting it up with my hand at a constant speed upward. And we said, well, then what would that look like? Well, once again, we're going to start off by drawing a free body diagram. And what forces are acting? Well, there's mg down. And this time there's still a normal force, but it's being applied by my hand. And I was intentionally ambiguous on the lengths of these because we're going to figure out exactly what's going on there. But the normal force is definitely up. And then we chose a positive direction. We went with up this time just because it was moving up. And so then we wrote our FNet statement. And the sum of all forces acting in the vertical direction, if up is positive, then our up force is normal, our down force is mg, so I do normal minus mg. And then again, after I've written an FNet statement based on my free body diagram, now I can substitute, use Newton's second law, substitute ma for FNet. And so ma equals n minus mg. And then here's the trick, right? It's being lifted up at a constant speed. And if it's being lifted at a constant speed, constant direction, then the acceleration is 0. And so once again, we find that the normal force is equal to the gravitational force. And for most first-year students, this is quite surprising, right? You think that the ball's moving up, and therefore there must be a greater up force than down. And I remind you, you're in good company, right? Aristotle thought the same thing. But Galileo and Newton demonstrated to us that that's not the case, that once the ball is started moving up, it wants to continue up, and so you just have to push as hard up as gravity is pulling down to keep it moving at that same speed. And so lifting up at a constant speed is the same as being at rest as far as the forces go. All right, and so then we moved from just the ball being in my hand or on the table, and we tossed it upward and then asked what would it look like on its way up. In other words, after it's left my hand on its way up, before it reverses direction and comes down, what would the free body diagram look like there? Well, once it's out of my hand, there's only one force, and that's mg. And so now there is an acceleration, and so we're going to choose the direction as positive that the acceleration's in, which is down. And then we're going to write our F-net statement based on our free body diagram. So what is the sum of all the forces acting in the vertical direction? Well, it's just the one force, mg. And then after I've written my clear F-net statement, then I substitute ma for F-net according to Newton's second law, and I get ma equals mg. Now we paused here because especially College Board loves to make this distinction. We asked ourselves, are those two m's on both sides of the equations the same thing? And it's a bit of a tricky question because in reality, technically they're not the same thing. On the right is what we call the gravitational mass, which relates how hard gravitational force pulls on an object in a gravitational field. And the one on the left is what we would call the inertial mass. In other words, how much the mass resists changes in its motion, or how much it resists acceleration. And those don't necessarily, I mean, there's nothing fundamental that says those two have to be the same. But it turns out that through experimentation over and over again, we've demonstrated that even though they don't have to be the same, they are fundamentally the same amount every time for every object. And so we can safely cross them out on both sides. And we see just what we learned in our first experiment of the year, and that is that the acceleration is completely independent of the mass once a ball or an object is in free fall. And that no matter what the mass is, the acceleration will always be 10 meters per second squared towards the center of the Earth. And so then, of course, we said, well, then what about after it turns around and starts coming down? What will the free body diagram look like then? And the answer is it looks just like this one. The acceleration is still down, but because now the velocity is reversed direction, it's speeding up instead of slowing down. And then, of course, finally, what about at the very top as it reverses direction? Does the free body diagram look any different? Are there any new forces or any forces missing? And the answer is no. It's the exact same free body diagram. The only force acting is gravity, and so the acceleration is still g. And of course, that brings up another point we want to make, and that is if you did velocity versus time for down being positive, you would get a result that looked like this. It started off going up, so it started in the negative direction, and then at the top it reversed direction and started coming down. Many of you got this right on the exam, right? And so let's look at it. That means that at this point in the middle, where it changed direction, the velocity instantaneously was 0 as it reversed directions, but the acceleration was not 0, right? Because it's in the act of changing direction, the velocity is constantly changing. The acceleration is not 0, and more specifically, it's 10 meters per second squared down. Incidentally, we also pointed out that this lowercase g symbol that we've used and we've referred to as the acceleration due to gravity, we have another way of referring to that. Oftentimes, we'll refer to that as the gravitational field strength, and we'll elaborate more on that third quarter, but I just wanted to point it out here. Because it has the same connection of, right, this relationship between the gravitational and inertial masses. All right, and then finally we said, hey, let's take that ball and look at what forces are acting on it right before it leaves my hand. Well, still gravity down, but now there's a normal force up, and notice, as I sped the ball up in order to launch it up in the air, my normal force in my hand had to be larger than gravity. In other words, in order for there to be an acceleration upward, I had to push up on the ball with a greater force than gravity was pulling down. That resulted in a net force in the positive direction, which resulted in the acceleration, and so I'm going to make up as positive. I'm going to write my F-net statement in order to answer this question. If I said that I pushed up with a constant force of 7 newtons, what was the acceleration of the ball? Well, let's answer it. F net statement in the y direction is up is positive, therefore it's normal minus mg. Just like I've done every time before, drawn the free body diagram, written the F net statement, and now that I have a good solid F net statement, I'm going to substitute ma for F net, and I get ma equals normal minus mg. However, this time the acceleration is not 0, so I'm not going to cross it out, but I am going to solve for the acceleration. The way I do that is I divide both sides by mass, and I just have to take normal minus mg divided by the mass will give me that acceleration. Well, what is the normal? It was given as being 7 newtons. What is mg? It's 1.4. And what's the mass? 0.14, for a total of 40 meters per second squared. So again, we take the scenario, we draw a free body diagram that has all the real forces acting clearly labeled. Also, we should have made this clearer earlier, but notice that we didn't draw any velocity vectors or acceleration vectors on our force diagram, for our free body diagram. You only draw forces on a free body diagram. The acceleration is implied because it's in the same direction as the total or overall net force of all the forces you draw, but you never draw a velocity vector on a free body diagram. And this is the hardest thing for new students, is they think if the ball's moving up, then there must be some kind of upward force. In this case, in the previous case, when the ball was on its way up or on its way down, there wasn't an upward force any longer, right? It had left my hand. There was only a downward force, and that's why the acceleration was down, even though the velocity was up. So again, just be careful. Only draw actual forces, real forces, on your free body diagram. Designate a positive direction and write a clear F net statement, and then substitute ma for F net, and then keep solving. All right, and then just for clarification, someone asked, for how I got the 7 minus 1.4, and so here's just a quick explanation of that. It was given that the normal force is 7 newtons, and so that was given information. And then mg, once again, remember we said that the mass of the baseball was 0.14 kilograms, and so if I multiply by 10, I get 1.4 newtons for the weight. And so that's where we got those numbers that we substituted to get to the 40 meters per second squared.